University. I'm here today to share some of my work in the identification system design for the operational load of the freight train with you. The first part is the background. As we know, railroad transport is one of the main modes of modern cargo transportation, which can realize long-distance transportation of goods across regions and is of great significance for optimizing the allocation of resources in the region. By virtue of its large capacity, high efficiency, low energy consumption ratio, and many other advantages, heavy haul transportation has gradually become the main mode of land transportation for bulk cargoes, such as coal and ores, and has been highly valued and developed in countries around the world since 1950s. Statistical data show that heavy haul transportation for coal and other bulk cargo transport costs for road transport is about 25% to 30%. Energy consumption is about 7%. Per billion converted ton-kilometer accident loss amount is about 1.3%. Heavy haul transport is recognized by our country and even the world's most sustainable development of land transport, but also the mainstream direction of the development of modern railroad freight. At present, China has built a number of special heavy haul transport lines, such as the Daqing, Shenhua, and Wari. Compared with foreign heavy haul transportation system, China's heavy haul railroad wagon axle weight is generally small, but China's heavy haul train running density is very high. The annual freight volume ranks first in the world. The Daqing line has created a single railroad annual capacity of 451 million tons of the world record, making China's heavy roads have become the world's busiest railroads. In recent years, China's heavy rail transport technology continues to make breakthroughs, has completed the 30-ton axle weight and 30,000 tons of grouping. At present, with the further increase of the load of heavy haul train, the coupler receives a large load and the load action direction is complex in the process of train operation, especially in the process of starting, braking, and crossing curve. It is easy to break the coupler path like the picture shows and cause major traffic accidents. At present, the existing force measuring couplers only pay attention to the longitudinal force in the process of train operation, ignoring the lateral force in the process of passing the curve and the vertical force in the process of going up and down the ramp. In addition, the use of wired monitoring is not conducive to train formation and loading or unloading of goods, while the use of wireless signal transmission needs to overcome the challenges of long transmission distance. To solve the above issues, we propose a multiple load identification system for heavy trains using LoRa wireless monitoring method. The work we have done can be divided into three parts. Firstly, the fault model of the coupler is theoretically analyzed by using the theory of classical material mechanics. The calculation relationship between the force received by the coupler and the surface strain of the coupler body is obtained, and the load identification coefficient matrix is obtained. Then we get the unknown coefficients in the load identification matrix through simulation calculation. Then we designed a strain bridge method which can collect the force in three directions of the coupler, and self-temperature compensation is considered. And we developed the model machine and carried out the calibration test and the verification test. Finally, we designed a wireless signal collection and transformation system. I will explain each part separately next. The first part is the construction of theoretical model. we have built two theoretical models. One is the longitudinal centripetal loading condition without considering the additional bending moment caused by longitudinal load. And when built, the theoretical model will mainly focus on the calculation relationship between the surface strain of coupler body and the three-dimensional load received by coupler. According to the theory of classical material mechanics, there is a linear relationship between strain and force. Therefore, under the condition of longitudinal centripetal load, we assume three coefficients, the CFL representing the relationship between the longitudinal load and the strain caused by the load, and CFH representing the relationship between the strain caused by lateral force and lateral load, and CFV representing the relationship between the strain caused by vertical force and vertical load. After derivation, we get the load identification coefficient matrix composed of these three coefficients. Then we developed the model machine as shown in the left figure. The model machine has three outputs, which are used to identify longitudinal force, lateral force, and vertical force respectively. In addition, we also carried out calibration tests and random loading verification tests, as shown in the figure on the right. We used number 13 coupler and number 16 coupler to carry out the test. This is a loading test machine we used to apply longitudinal load. We also used the two hydraulic loading machine to apply vertical load and lateral load respectively. We also designed a reaction frame to help us load the lateral force. In order to obtain the coefficient in the load identification matrix, we carried out the calibration test, applied the longitudinal load from 100 kN to 500 kN to the coupler respectively, and then applied the lateral load and the vertical load from 10 kN to 50 kN to the coupler respectively, with the longitudinal load of 500 kN. The linear relationship between the load and the coupler body strain is obtained, and the coefficient in the load identification matrix is obtained by fitting the curve. And in order to verify the correctness of our load identification matrix through experiments, we also carried out random loading verification tests. We applied 10 groups of random loads to the coupling coupler to obtain the surface strain of the coupler body. Then substitute the identification strain into the established load identification matrix to calculate the load on the coupler, and compared the given load with the identified load. It is found that the identification error of the load identification matrix designed by us is less than 2 kN, and the identification effect meets the needs of engineering application. The second part is the strain gauge design. We designed the load identification bridge by install a protective plate on the bottom to block the beam and preventing the beam from damaging the bottom strain gauge. The strain bridge corresponding to this design scheme is shown in the figure. This is the bridge combination used to identify the load, the longitudinal load. It can be obtained by deriving the relationship between voltage and strain. The bridge has the function of temperature self-compensation. These four items shown here represent the temperature self-compensation function of the top surface, bottom surface, right surface, and left surface respectively. This is the bridge combination used to identify the lateral load. These two items respectively represent the temperature self-compensation function on the left and the right surface. This is the bridge combination used to identify the vertical load. These two items respectively represent the temperature self-compensation function on the bottom surface and top surface. For the strain bridge we designed, we verified the temperature self-compensation function. We used a high-power incandescent lamp to eliminate the coupler body surface strain gauge to simulate the uneven temperature of the four surfaces sunlight. Collected the temperature with a resolvable temperature test paper and collected the strain output of the bridge with temperature compensation function with a data collector. In addition, in order to compare with the function of our bridge, we also put a bridge without temperature compensation on each of the surface. From the result in the right figure, we can see that after the irradiation of the high-power incandescent lamp, the output voltage of the bridge without temperature self-compensation function, like this one, shows that changes accordingly with the temperature. Well, the output voltage of the bridge with temperature self-compensation, the blue one, designed by us, is basically unchanged. After conversion, the zero drift strain output of the temperature compensation bridge is less than 12 microstrain. It is equivalent to that the load identification error is less than 3 kilonewton. I will introduce the signal transfer system in this part. First, let's look at the typical Chinese heavy haul train. Typically, the locomotives here use number 13 coupler. The open wagons are in groups of 3. Each group is connected by number 17 coupler, and the 3 wagons in each group are connected by traction by the drawbar. In China, the length of a 20,000 ton train can reach more than 2,600 meters. The different dynamics are exhibited at different locations of the train. Therefore, we designed the submodel here arranged at the middle, at the head, and at the tail of the train. And each submodel consists of a force measuring coupler and a set of data acquisition and transmission devices. The acquisition frequency of the submodule is 166 Hz, and a flash memory card is used to data storage. Since there is no power supply in the open wagons, a battery is used to power the submodule. The terminal here is placed in the driver's cab at the locomotive location and receives data from the submodule every 5 seconds, which can provide the driver with coupler force information to adjust their operation. And because there is no power supply in the wagons as we said before, we also consider using wind power or solar power to charge the submodel in the future. The third part is prospect of our research. The first prospect is that we would like to conduct long-term tests of coupler load on heavy haul trains. Through the multivariate coupler load tracking and monitoring of up and down ramps, small radius curves, and other working conditions, on the one hand, it can provide traceable data for accidents such as uncoupler and coupler breakage during transportation, and provide supports for dynamic analysis. On the other hand, real-time monitoring of the coupler load can provide a basis for astronomical control of the air brake of the vehicles of large groupings, and can also provide a load spectrum for the fatigue damage assessment of the coupler structure and the development of crack and breakage. Second is apply the method to other type of trains. The intercity trains and mainline high-speed train use tight lock couplers, unlike the couplers used for freight trains. The tight lock couplers do not allow two couplers to produce relative displacement in the vertical direction. By laying the differential strain gauges at the key stress position of the tight lock couplers and performing bridge design, the multivariate load decoupling identification of the tight lock couplers can be realized, and the dynamic analysis can be done. That's my presentation. Thank you for your attention.
Thank you very much, Yazhao, for such a wonderful presentation. So we'll take questions from the audience, if there are any. So if you want to ask a question, you can write the question or raise up your hand, and then I will allow you to talk. Meanwhile, Yado, I have a question. Can you tell us the main difference between, or is there a difference between the coupler of a passenger train and the coupler of a freight train?
Okay. As we showed here, in the for the high-speed train used now in China, the coupler, the coupler body is, as you can see here, is sorry. As you can see here, it's cylindrical. It's round. It's a round body. So we cannot use the same design for the freight train because freight train has four surface. It's a square. It has four surface. But for the passenger train, it's a round surface. So we cannot use the same design for the freight train here. We have considered this problem before. We want to monitor the torque string on the passenger train coupler to identify its load.
All right, thank you. So from the audience, is there anyone who wants to ask a question? So I'll wait for 5 seconds. And after 5 seconds, I will assume that there are no questions. Okay, in the absence of any other questions, I would like to, on behalf of all the students who have joined in, to appreciate and thank you, Wang Yazhao, for sharing your knowledge and sharing your time and energy with us. Thank you very much for your wonderful.
Okay, thank you. Thank you,
And
Ali.
yes, for the audience, if you have questions, his email is on the screen. You could send him a direct email. Thank you very much, Yazhao, for the presentation.
Thank you. Thank you too.
You're welcome. Okay, guys, this is the end of this session. And by 2:30, there will be another presentation session. So we hope that you join and listen to what the speaker has to say. Thank you very much, everyone. And this is the end of this session. Bye.